Welcome everyone. Today brings us to determinants. This is section 3.4, though we're going to have a little bit of 3.6 sprinkled in at the end. In fact, I think I'm going to make this 2 videos, so I'll stop in the middle of 3.4 and we'll do 3.6 in a second video so that this is not too long. Key terms, determinants, cofactors. Okay, all we're going to be doing is taking the determinant of square matrices. In fact, that's the only determinant you can take of is square matrices. The determinant is denoted DET and whatever the matrix is called. So in this case, it's the determinant of A, but if I had a matrix B, it'd be the determinant of B, DETB. It's a measure of how associated the rows and columns are. Okay, so if you look at the matrix 1, 2, 10, and 20, you can see that the rows of the matrix are highly related to one another. The row 2 is a scalar multiple of row 1. And when we compute the determinant, when I teach you how to do that, of that matrix, you get a determinant of 0. And so that is meant to tell you that the rows are related to one another. Whereas if you take the determinant of 1, 2, 10, 21, where row 2 is not a scalar multiple of row 1, then you can see that determinant is going to be non-zero. So what is the determinant of a 2 by 2 matrix? You take the product of the diagonal, subtract off the product of the off diagonal. So A11 times A22 minus A21 minus A12. So if we're going to take the determinant of 3, 2, 1, 4, that's 12 minus 2, which is 10. If we were to take the determinant of 2, 8, negative 1, negative 4, we would get minus 8 minus a negative 8, and that is 0. Okay, so we just made that comment above that whenever the determinant is 0, the rows and columns are related to one another. What's the relationship here? Well, it looks like if I were to multiply row 2 by what? Negative 2, I would get row 1. Okay, there you go. Now, to compute the determinant of A of something that's more than a 2 by 2 matrix, you have to do a little bit more work. Okay, you need to know what cofactors are. Okay, so to compute the cofactor Cij, what you have to do is delete Aij's row and column, and then take the determinant of the remaining matrix multiplied by negative 1 raised to the I plus j. Okay, so what does all that mean? Okay, so first off, look at C11, the cofactor for location A11, that's 3, okay? You're going to delete that row and column. So cross out 3, 5, 7, cross out 3, negative 1, 6. Okay, I can cross them out. Well, I don't know if that shows up well, but you're going to basically do this. What are you left with? You're left with 2, 4, 3, and negative 2. Okay, take the determinant of that. That's negative 4 minus 12, that's negative 14. And you multiply it by negative 1 to the row 1 plus column 1, so that's negative 1 squared. And so the cofactor is negative 14. If we're to do this for row 2, column 3, okay, so row 2, that's right there, column 3, so you're going to cross out the row and column. That 4 is in. You're left with 3, 5, 6, 3. Okay, take the determinant of that. And you get what? 9 minus 30 times negative 1 to the 2 plus 3 power. So that's negative 1 to the 5. So that's negative 1. So 9 minus 30 is negative 21 times that, that's positive 21. Okay. Now we can compute the determinant of A by summing up all the cofactors across a particular row or column. Okay, I'm going to show you kind of the, I don't want to call it the easier way, but it's the way that I was taught. So let's look at this. The matrix 3, 5, 7, negative 1, 2, 4, 6, 3, and negative 2. Pick a row or column in which you want to expand across. Okay, here's what I mean when you expand across. Okay, I'm going to take the first row. I'm going to expand across that row. So that means the determinant of A is going to be found taking the determinant of 3 2x2 matrices, one for each element in row A. So looking at 3, okay, you take 3, multiply it by the determinant of the leftover 2x2 matrix. So cross out the row that 3 is in, cross out the column that 3 is in, you're left with the 2, 4, 3, negative 2. We computed that up there. Okay, but now do the same for 5. So now cross out the row that 5 is in and the column that 5 is in. You're left with negative 1, 4, 6, and negative 2. And lastly, the row and column that 7 is in. You get negative 1, 2, 6, and 3. Hopefully that's all showing up. It's probably a little bit too tall there. All right. Okay. Now, take the coefficients, 3, 5, and 7, multiply them by the determinants, and the last thing you have to do is write the plus or minus. Okay? So, this is cell row 1, column 1. So, this would be negative 1 to the 1 plus 1 power. That's positive. This is row 1, column 2. That's negative 1 to the 1 plus 2 power. That's negative. This is row 1, column 3. That's negative 1 to the 1 plus 3 power. That's negative 1 to the 4th. That's positive. So those are the coefficients on 3, 5, and 7. And we compute the determinant. 2, negative 2, that's, well, this is 3. That's minus 4, minus 12. Did I get the first one wrong? I guess I did. This right here. This is negative 4 minus 12. That's negative 16. Sorry about that. All right. So negative 4 minus 12, that's negative 16. Minus 5 times, that's positive 2 minus 24, plus 7 times minus 3 minus 12. So we get 3 times negative 16 minus 5 times negative 22 plus 7 times something, negative 15. So that's negative 48. That's positive. It's 110, and that's minus 70 plus 25 is 105. So minus 43, okay, is the determinant of that matrix. Now, the good news is, if we wanted to expand across a different row or a different column, we could do that as well. Let's pick the same example, okay, and let's go down column 2, okay, instead of across column, row 1. We should get, provided that I do the arithmetic right, the same determinant. Let's see. So if I go down column 2, here's my 3 2x2 matrices. I cross out the row that 5 is in, along with the column. you're left with what? Negative 1, 4, 6, negative 2. Negative 1, 4, 6, negative 2. Now I cross out the row that 2 is in. So I'm left with 3, 7, 6, negative 2. And cross out the row and column that the 3 is in. So that's 3, 7, negative 1, 4. The coefficients here are 5, 2, and 3. Okay, this is, the 5 is in row 1, column 2, so that's negative 1 to the 1 plus 2, that's negative 1 cubed, so that's a minus. Let's put a negative sign there. This is row 2, column 2, so negative 1 to the 2 plus 2, that's positive. And this is negative 1 to the 3 plus 2, row 3, column 2, that's negative. So minus plus minus. And let's make sure we get negative 43. So this is minus 5 times 2 minus 24 plus 2, that's negative 6 minus 42 minus 3 times 12 plus 7. So that's negative 5, negative 22. We got that to be 110. We have 2 times negative 48. That's minus what, 96. And we have minus 3 times 12 plus 7. That's 19. So that's negative 57. So 4 and 10, so that's 14 minus 57. I'm going to assert that that's negative 43. All right. So, as you can see, if I expand across the first row, I get negative 43. Down the second column, I get negative 43. If I would have done any other row or column, I would get the same answer. All right, back to the notes. Let's do this 3 by 3. The determinant, let's call this matrix something other than A. Let's call it B. So if I were going to take the determinant of B, what I would like to do is I would like to expand down the second column. Okay, why the second column? Well, look, there's a bunch of zeros in it. So when you set up your determinant, okay, you're going to multiply the first matrix by 0, the second matrix by 4, the third matrix by 0. The signs will go minus, plus, minus. But does it really matter what's in this matrix or in this matrix? No, it really doesn't. I mean, really what goes in this matrix is 2, 2, 1, 1, 3, and what goes in this matrix is 3, 2, 2, 1. But I'm going to multiply that by 0 anyway, and so that drops off. So the only thing that really matters is what happens when I cross out the row and column that 4 is in. 3, 2, 1, 3. So I compute this determinant, and I get to be 4 times 9 minus 2. That's 28. All right. So some of these matrices will have built-in efficiencies in how to compute the determinants. Just look for them, okay? What about this one? Well, this one doesn't. There are no zeros there, okay? But I think you're going to get an interesting result out of this. So let's call this matrix C. Let's compute the determinant of matrix C. Since there's no zeros anywhere in the matrix, I'm going to expand across the first row. Okay, so matrix 1, matrix 2, matrix 3. This is 1, 2, and 3 out in front. And the signs are positive, negative, and positive. Again, you're looking at row 1, column 1. 1 plus 1 is 2. Negative 1 squared is positive. Then negative, then positive. Okay. What goes in each of the matrices? So cross out the row and column. You're left with 5, 6, 8, 9. Cross out the row and column that 2 is in. You're left with 4, 6, 7, 9. Cross out the row and column that 3 is in. You're left with 4, 5, 7, 8. All right, let's see what we get here. So it's 1 times 45 minus 48, minus 2 times 36 minus 42, plus 3 times 32 minus 35. So this is negative 3. That's negative 6 times negative 2, so that's plus 12. And that's negative 3 times 3, so that's minus 9. What does that equal? It equals 0. So that means the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9 has rows that are related to one another, but none of them are scalar multiples of one another. It's not like I can multiply row 1 and get 4, 5, 6, because if I multiplied row 1 by 4, I would get 4, 8, 12, which is not 4, 5, 6. Same is true with row 7, 8, 9. So how are those related to one another? Let's see. Let's take row 3, which is the, quiet guys, which is, quiet, which is the row 7, 8, 9, okay? And I'm gonna say that's equal to 2 times row 2 minus row 1. I believe that's the relationship here. Because what's 2 times row 2? 2 times row 2 is 2 times 4, 5, 6 minus row 1, 1, 2, 3. What does that give me? That gives me 8, 10, 12, minus 1, 2, 3. 8 minus 1 is 7. 10 minus 2 is 8. 12 minus 3 is 9. And that is what row 3 is. Pretty good. Okay, so you can see that there is a relationship between rows 1, 2, and 3 of that matrix. All right. So let's go through the properties of the determinant, and then we can call it a day. The determinant of the identity matrix is 1, and it doesn't matter if it's a 2 by 2 identity matrix, 3 by 3, 4 by 4, 5 by 5. The determinant of any identity matrix is 1. When you swap a row in the determinant of a matrix, so let's say I have the matrix 1, 2, 5, 4, 5, 6, 7, 8, 9, and notice that I'm not putting a 3 here. And I wanted to compute the determinant of 1, 2, 5, 7, 8, 9, 4, 5, 6. So I'm swapping rows 2 and 3. How are their determinants related? Well, one is a negative of another. Okay, so the determinant that you obtain by swapping a pair of rows in a matrix is negative the determinant of the original matrix. What about scalar multiplication? So if you take the determinant of one row scaled, okay, so let's take row 2, multiply it by 10, okay, that's going to be 10 times the determinant of 1, 2, 5, 4, 5, 6, 7, 8, 9. If I were to have scaled every row, so that's 10, 20, 50, 70, 80, 90, this would be 10 cubed times the determinant of 1, 2, 5, 4, 5, 6, 7, 8, 9. And for sums, if row 3 was the sum of two other vectors, C and D, then the determinant of A1, A2, C plus D is the determinant of A1, A2, C plus the determinant of A1, A2, and D. Okay. Moving forward. The determinant of an upper triangular matrix is the product of the diagonals. Okay, so this is an upper triangular matrix. So the determinant is 3 times 5 times 7 times 11, whatever number that is. It doesn't matter what any of the numbers are in the upper diagonal or upper triangle. If any of the rows of the matrix are all 0, then the determinant is 0. Okay, so pairing that up with the comments that I made at the beginning of the video, that means one of the rows is a scalar multiple of the other. That's an easy one to see. Okay, row 2 is 0 times row 1. Okay, that makes sense. Let's keep moving forward. Property number 5. If any two rows are identical, then the determinant of A is 0, because row 2 equals row 3, then means they're related to one another. So if the determinant is measuring what I claim it's measuring, then the determinant should be 0. If I have two matrices, A and B, and I take their product, the determinant of the product is going to be the product of the determinants. So the determinant of A times B is the determinant of A times the determinant of B. So consequently, if we take the determinant of A is 4, then the determinant of A inverse is what? Well, let's see. A times A inverse is the identity matrix. Using this property, the determinant of A times A inverse is equal to the determinant of the identity matrix, which we know to be 1 by property number 1, but this right here is the determinant of A times the determinant of A inverse, which we know is going to be 1, and this is 4, so the determinant of A inverse is a 4th. Keeping going, the determinant of A transpose is the determinant of A. So you can swap all the rows and columns and the determinant will not be affected. So that means every time I said row in the previous set of properties, okay, that thing that I said about rows also applies to columns. If the rows of a square matrix are the vectors of a parallelogram in a 2x2 case or a parallelepiped in a 3x3 case, then the determinant of A is representing the area of the parallelogram or the volume of the parallelepiped with a plus or a minus. So you take the absolute value, you get the determinant of that. Okay, so just to give you a quick visual, okay, the determinant of vector 1, vector 2, okay, if this is vector 1 and this is vector 2, okay, this is the resulting, that's not quite parallelogram, but there we go, something like that. The area of this parallelogram that's obtained by vector 1 and vector 2 is going to be the same as the determinant of V1 and V2. All right. Minus a plus or a minus sign. Determinant of A is 0, then A is a not invertible matrix, which means AX equals 0 has many trivial solutions. Okay, if determinant of A is 0, then A is invertible, and AX equals 0 has only the one trivial solution. Well, what trivial solution are we talking about? That's going to be the only way to output a 0 resultant vector is to input a 0 resultant vector. Okay, so I'm going to stop on number 9. I'm going to let you think about that until the next video, but that should get you going on section 3.4. We have a couple more problems left, okay, and then we'll jump into Cramer's rule, which is what section 3.6 is about. Okay, but this will get you going, and the video is probably long enough as it is. Take care. Have a good one.